This lecture outlines the formation of the moon and is derived in part from the Moon Formation Processes slideshow compiled by the Lunar Planetary Institute. Through comparative planetology, we organize observations that must be explained by any theory that describes the origin of the moon. This photo shows the Earth-Moon system was taken on December 16, 1992, when 8 days after its final encounter with the Earth, the Galileo spacecraft looked back and captured this remarkable view of Earth and Moon. The image was taken from a distance of 6.2 million kilometers. The picture was constructed from images taken through the violet, red, and 1-micron infrared filters. The moon is in the foreground, moving from the left to the right, and the brightly colored Earth contrasts strongly with the moon, which reflects only about 1/3 as much sunlight as the Earth. Contrast and color have been computer enhanced for both objects to improve visibility. Antarctica is visible through the clouds at the bottom. The moon's far side is seen. The shadowy indentation of the lunar dawn terminator is the South Pole Aitken Basin, one of the largest and oldest lunar impact features. The Earth's radius is about 3.7 times the moon's radius. The density of the Earth is also higher than the density of the moon. The moon has no atmosphere, so the temperature changes greatly throughout the day, which is 29.5 Earth days long, the same duration as its orbit around the Earth. The Earth has a molten interior that gives rise to a magnetic field as it rotates. The core is very hot. The mantle of the Earth is active and leads to tectonism, earthquakes, and volcanism. The interior of the moon is cool and has no magnetic field, and there are only small moonquakes. The moon has bright regions, the old highlands, which are heavily cratered, and young, darker regions, the basalt seas, which have fewer craters. The old highland rocks date back 4.5 billion years. The moon formed a magma ocean during its formation due to the sources of heat, impact, internal compression, radiogenic decay, and gravitational tides. We know this because when the first moon rocks were brought back to the Earth during the Apollo program, they were composed almost entirely of one mineral, feldspar, which is only formed by the precipitation of crystals from a molten lava to separate the crystals according to differences in density, a process known as fractional crystallization. Here, feldspar crystals initially crystallized with other materials and then floated to the surface of a large magma pool. The denser minerals sank and the less dense minerals floated. Eventually, the rocks cooled and solidified, leaving a crustal surface dominated by feldspar, and the rock would be anorthosite. We observe this separating of minerals by density in magma chambers within the continental crust on Earth. On the moon, this process is huge, with an anorthosite crustal thickness estimated to be 20 kilometers, implying that the magma ocean was once 1,000 kilometers thick. So far, the measurements of anorthosite using radiometric techniques indicate that the crustal thickness solidified 4,400 million years ago, only 200 million years after the formation of the solar system. So the question we want to answer is, how did the moon form? Some of the relevant observations are the similarities and differences of the moon and the Earth and other planets. The moon has a density of about 3.3 grams per cubic centimeter. This is low compared to Earth's, which is closer to 5.5 grams per cubic centimeter. The moon is enriched with titanium, aluminum, and related elements, and depleted in iron and volatile elements and compounds. It is very dry. Angular momentum is a measure of the rotation in a system. The Earth and the Moon system has an anomalously large amount of angular momentum compared to other planets. The formation of the Earth and the Moon system has to obey the conservation of momentum. Momentum is the product of mass and velocity. Angular momentum is the product of mass and velocity along circular motion. The Earth's high angular momentum can be explained by impact that created the moon, resulting in a higher momentum for the whole system. The combined momentum of these two closely related bodies must stay the same over time. If the moon is closer earlier, then the Earth must have been rotating faster. In other words, we had shorter days. The three main models of the formation of the moon at the time of the Apollo program all failed. The first failed theory was that the moon and the Earth formed at the same time. This theory failed because it could not explain why the moon lacks iron. A second early idea was that the moon formed somewhere else in the solar system where there was little iron and then was captured into orbit around Earth. This failed when lunar rocks showed the same isotope composition as the Earth, so the Earth was too much like the moon. Furthermore, there were problems with orbital mechanics due to moon capture. A third early idea was that the early Earth spun so fast that it spun off the moon. The moon spun off the Earth during Earth's differentiation. Pacific Ocean, they thought, was a hole left by the moon. The idea would produce a moon similar to Earth's mantle. The theory failed because the moon could not reach escape velocity, and the total angular momentum would not be conserved. These theories do not explain the observations. The moon was formed as the result of an impact by a Mars-sized object now called Theia on the protoplanet 4.31 billion years ago. The impact hypothesis explains the difference in composition, the difference in relative sizes, the chemistry of the Earth and the Moon, the orbits of the Earth and Moon, the high angular momentum of the Earth-Moon system. According to the giant impact hypothesis, Theia orbited the Sun nearly along the orbit of the proto-Earth by staying close to one or the other of the Sun-Earth systems, two more stable Lagrange points, but eventually it was perturbed away from that relationship by a gravitational influence of Jupiter or Venus, resulting in the collision between Theia and Earth. Originally, the model called for a glancing impact. In January 2016, UCLA's Stuart Wolpert published evidence that the impact was head-on and that Theia's remains can be found on both Earth and the Moon. According to the Lunar Planetary Institute, the energy from the Moon's initial formation caused at least the outer few hundred kilometers of material to melt. This is known as the magma ocean stage, literally a deep ocean of molten rock. This solidified during the first 50 to 100 million years of lunar history. This diagram depicts the magma ocean concept. When the moon formed, it was enveloped by a layer of molten rock called magma, hundreds of kilometers thick. As the magma crystallized, the minerals more dense than the magma sank, while those less dense, such as feldspar, floated, forming the anorthosite crust. The dense minerals, olivine and pyroxene, later remelted to produce the basalts that compose the maria. The lunar magma ocean cooled and crystallized, forming a crust about 60 kilometers thick. Asteroids continued to bombard the moon, leaving impact craters. 4 billion years ago, the moon had many craters but no maria. By 3 billion years ago, the maria had formed, and now the maria are covered with craters. These are two examples of rocks that crystallized from the lunar magma ocean. Both are made primarily of the mineral plagioclase, which gives the lunar highlands its light gray color. The troctolite also contains some greenish olivine grains. This sample of anorthosite on the left was returned by the Apollo 15 mission. Anorthosites are composed almost entirely of one mineral, plagioclase feldspar. They also contain smaller amounts of olivine and iron oxide and pyroxene. One way a single mineral rock forms is by accumulation by either floating or sinking in magma. Because anorthosite seems to be abundant and widespread type of rock on the lunar highlands, scientists have concluded that at one time the moon was surrounded completely by a huge ocean of magma shortly after it formed. The highlands are light, rough, and mostly anorthosite. These rocks formed in place about 4.5 billion years ago. Anorthosite makes up about 60% of the Earth's crust as well. Both the Earth and the Moon were struck by numerous asteroids and comets in their early history. These impacts produced deep basins up to 1,000 kilometers across, surrounded by high rings of mountains on the Moon, and are visible to the eye as prominent circular structures. On the left is a view of the mountains that surround the Imbrium impact basin. The smooth, dark region on the right of the image is the younger lava flows. On the right, you see three mountain rings surrounded the Oriental impact basin. Both the Imbrium and the Oriental impacts occurred around 3.8 billion years ago. Energy from the impact fragments the original lunar rocks and compresses them into new, complex rocks known as breccias. Sometimes portions of the rock melt and resolidify, which allows the age of the impact to be measured using radiometric dating methods. The deep part of many large impact basins were later filled by eruptions of basaltic lava. This forms the circular Mare Imbrium on the left image. At the right, shadows reveal the edges of a long lava flow from the lower left to the upper right of the image. The volcanism in Mare Imbrium occurred about 3.3 billion years ago. Being small, the moon cooled quickly and was mostly dead volcanically by 3 billion years ago, although limited volcanism in some isolated regions is thought to have occurred as recently as 1 to 2 billion years ago. And more recently, geologists are considering even younger volcanism. Portions of the moon's interior remained hot enough to produce magma for more than 1 billion years after it formed. The molten rock flowed onto the lunar surface through the cracks in the crust, spreading out and filling the low regions in the impact basins. As the lava cooled, it formed fine-grained dark rocks called basalt, and these were also sampled and brought back from the Apollo missions. The dark areas were dating back to 4.2 to 1 billion years ago. At that point, the moon is thought to have become geologically inactive. Lava tubes are natural conduits through which lava travels beneath the surface of the lava flow. Tubes formed by crusting over lava channels and Pahoehoe flows. A broad lava flow field often consists of a main lava tube and a series of smaller tubes that supply lava to the front of one or more separate flows. When the supply of lava stops at the end of an eruption, lava is diverted elsewhere. Lava in the tube system drains downslope and leaves partially empty conduits beneath the ground. Such drain tubes are commonly exhibit the high lava marks on their walls and generally flat floors, and many lava stalactites that hang from the roof. Lava can also erode downward, deepening the tube and leaving empty space above the flowing lava. Rare volcanic domes and rills, which are lava channels formed. Volcanism is believed to have finished by 1 billion years ago, though new studies suggest that it may have ended more recently. Although eruption of most Mare basalts did not produce volcanic mountains, there are a few small volcanic domes in a few places. This shows the Marius Hills, a collection of relatively low domes. Rills, the sinuous lava channels, are also visible, one of which cuts across a Mare ridge. Basalt is a fine-grained, dark, igneous rock rich in iron and magnesium, basically the stuff that sank in the magma ocean. The dark, smooth maria are a few hundred meters thick. These rocks are typical of lunar volcanic rocks. Collected by Apollo 15, both are 3.3 billion years old basalt, similar to those produced by volcanoes such as Hawaii on Earth. The lower image contains some type of gas, possibly carbon monoxide, which formed the round holes known as vesicles. The basalt rocks are 4.3 to 3.1 billion years old, meaning volcanic flows as recently as a billion years ago. Comparing our volcanic rocks, the basalts on the Moon are clearly formed under different environmental conditions and have different chemistries. The Earth is constantly resurfaced by wind and water erosion, impacts, volcanoes, and earthquakes. These erase evidence of cratering. There is active magnetic field and the Earth is alive. The Moon has no erosion processes, volcanoes, magnetic field, or substantial quakes to alter its surface today. There are many, many craters. The Moon is geologically inactive. Lunar geological history is divided into the following eras: the pre-Nectarian, Nectarian, Imbrian, Eratosthenian, and Copernican. From 4.55 billion years ago, the time of the initial formation of the Moon, to 3.9 billion years ago, when the Nectarian basin was formed by a large impact, the pre-Nectarian era lunar terrain is thought to have been dominated by the type of rock anorthosite, which suggests that the early stage of lunar crustation occurred via mineral crystallization of a global magma ocean. The partly molten Moon underwent crustal differentiation, the anorthosite being the least dense crustal composition rock eventually covered the outer surface, while the iron and magnesium sank to form the mantle and the iron nickel ore sank to form the core. Apollo astronauts did not find many examples of rocks from this era because the lunar highlands had been heavily churned, brecciated, and thermally affected by subsequent impacts, particularly during the late heavy bombardment that marks the approximate beginning of the Nectarian period. This image shows the Nectaris Basin, the creation of which marks the beginning of the late heavy bombardment period. The late heavy bombardment is an event thought to have occurred approximately 4.1 to 3.8 billion years ago. During this interval, a disproportionately large number of asteroids are theorized to have collided with the very early terrestrial planets in the inner solar system. The late heavy bombardment happened after the Earth and other rocky planets had formed and accreted most of their mass, but still quite early in the Earth's history. The Nectarian period of the lunar geological timescale runs from about 3.9 to about 3.8 billion years ago. It is the period during which the Nectaris Basin and about a dozen other major basins were formed by large impact events. Ejecta from Nectaris forms the upper part of the densely cratered terrain found in the lunar highlands. About 1,300 craters between 30 and 300 kilometers were formed during this era. Breccia, from Italian for loose gravel, is rock, composed of broken fragments of minerals, or rock cemented together by fine-grained matrix. Lunar breccias were created from impact cratering events. Impactors cause the Moon's surface rock to melt, and the melt cools quickly into glass or slowly into crystallized minerals. Breccia on the Moon are composed of fragments of anorthosite and gabbro and contain fragments of glass. From this period, it would be mostly anorthosite. The Imbrian basin formed from the collision of a protoplanet during the late heavy bombardment. Basaltic lava entered and flooded the giant crater to form the flat volcanic plain seen today. The basin's age has been estimated using radiometric dating techniques to be 3.938 billion years old, and its size has been estimated to be 250 kilometers in diameter. The lunar geological timescale, the early Imbrium epoch occurred between 3.85 billion to about 3.8 billion years ago. It overlaps with the late heavy bombardment of the inner solar system. The impact that created the huge Mare Imbrium basin occurred at the start of this epoch. The other large basins that dominate the lunar near side, such as the Crisium tranquillitatis, Serenitatis, Fecunditatis, and Procellarum, were also formed in this period. The basins filled with basalt mostly during the subsequent late Imbrium epoch. In the lunar geological timescale, the late Imbrium epoch was during which the mantle below the lunar basins partially melted and then they filled with basalt. The melting is thought to have occurred because of the impacts of the early Imbrium thinned the overlying rock, causing the mantle to rise because of the reduced pressure on it, bringing molten material closer to the surface, or the top melting as heat flowed upward through the mantle because of reduced overlying thermal insulation. The majority of lunar samples returned to Earth for study come from this epoch. The Eratosthenian period in the lunar geological timescale runs from 3.2 to 1.1 billion years ago, and it is named after the crater Eratosthenes, which displays characteristics typical of craters of this age, including a surface that is not significantly eroded by subsequent impacts, but which also does possess a ray system. The massive basaltic volcanism of the Imbrium period tapered off and ceased during this long span of lunar time. The younger lunar lava flows identified from orbital images are tentatively placed near the end of this period. Its Earth equivalent consists of most of the Mesoarchean and Neo-Archean eras, the Paleoproterozoic and Mesoproterozoic eras. The Copernican period in the lunar geological timescale runs from approximately 1.1 billion years to the present day. The base of the Copernican period is defined by the impact craters that possess bright, optically immature ray systems. The crater Copernicus is a prominent example of a rayed crater, but it does not mark the base of the Copernican period. Its Earth equivalents are the Neoproterozoic era and the Proterozoic eon, and the whole of the Phanerozoic era. So while animal life bloomed on Earth, the Moon's geological activity was coming to an end. This slide shows the comparisons of eras and eons on Earth, Mars, and the Moon. And here's a timeline of life, when life was forming compared to, for example, the various epochs on the Earth and Moon. Notice the LHB meteorites, that's the late heavy bombardment period, was happening about midway of where we saw just the single-celled life on Earth. In summary, the geological processes that shape the surface of the Earth and Moon are different. The current theory about the Moon's formation is the giant impact hypothesis, which states that the Moon was formed as a result of an impact by a Mars-sized object shortly after its formation of the Sun, when the Earth was still a protoplanet.